Physics 2211 Lab 2 over the motion of a falling object. In this lab, we use Newton's second law with the net force not equal to zero. The object is falling to the ground with a non-constant velocity indicating that there is an acceleration. The system is the ping pong ball and the surroundings is everything else. The equation we use for this lab is final velocity equals initial velocity plus F net over m times delta t. In this lab, we took a video of an object falling and got its position and corresponding times. Then we used a computational model to predict the motion of the object both with and without drag, and then we compared that with our observed data. Here are two force diagrams. On the left is the force diagram depicting the object if only the force of gravity was acting upon it. And on the right is the force diagram if there is drag force and the force of gravity. And as the velocity gets bigger and bigger, the drag force gets greater and greater until it equals the force due to gravity. We assume that there is the force due to gravity and the drag force acting upon the object. Here is my tracker video analysis. As you can see, I dropped a ping pong ball and I set the origin at the floor so the ball was falling towards the origin. And as you can see right here, the points are getting further and further away from each other, indicating that the ball is covering more and more distance and accelerating. Here is my y position versus time graph, and then here is my time values and my y values. As you can see, the ball is the system and the surroundings is everything else. Here's my glow script without drag. So as you can see, my gravity is negative 9.81, which is the universally accepted gravity. My drag constant is 0, meaning there's no drag. And as you can see, here is the velocity update formula and the position update formula. And to the right, you can see that here is my position graph, and then here is my velocity graph. Because there's no drag, it's a constant acceleration, and therefore my velocity is linear. Here's my glow script code with drag. As you can see, most things are the same. My position vector, which I didn't mention before, is 1.378. That is because that is my initial position in my tracker video. But the only difference right here is that I have a drag constant of 0.00297, and I found this out by inputting drag values until I got a graph that was representative of the data that I got in my tracker video. And as you can see, I updated with my force of drag is the constant times the ball's velocity squared, and that is the way we calculated out the force due to drag in this lab. Then here we have the F net calculated out, and then once again we have the velocity and position update formulas. Here's the graph of position versus time and the velocity versus time. As you can see, because there's a drag, the acceleration is changing, and thus the velocity is not linear. So here's my observed versus predicted graph. The blue is my observed data from tracker. The yellow is the predicted with drag, and the red is predicted without drag. As you can see, both the predicted graph without drag goes much further. That is because there's no force pointing in the opposite direction. However, with the simulated predicted values with drag and the observed values, you can see that they're slowing down and it's not at a constant acceleration, unless you can see that some force is acting upon the real observed object, and that the predicted values that predict for an object with drag better represent the data rather than a predicted value without drag. So here you can see I have plotted the y velocity versus time graph. The red is the y velocity versus time for my computational model with drag, and the blue is without drag. So as you can see, do either models predict a terminal velocity? No, neither model predicts the object approaching a terminal velocity. We can look at the slopes of both lines and determine that the velocities are still decreasing and thus have not reached a terminal velocity. In a graph scenario, when an object has reached terminal velocity, the slope of the velocity versus time graph will equal 0, and that is not the case for either line. If the object was thrown downwards initially, would the terminal velocity be same or different? Well, because the terminal velocity is not dependent on the initial velocity, the terminal velocity will be the same. This is because terminal velocity occurs when force due to gravity equals force of drag. Therefore, the terminal velocity will be the same. It just might reach it at different points in time due to the initial velocity. Thank you for listening to my lab.